In this video, I will demonstrate to you how to perform an analysis of variance and how to test, how to conduct post hoc test or do multiple comparison. The data set for this example will be the same as in a lecture presentation. A fashion psychologist investigated the effectiveness of 3 new store layout. So, and we have our standard store layout. So in total, 40 participants took part in a study with 10 participants only going into one store. So 10 went to standard, 10 went to the first store changed, the second went to the second store changed, and the fourth group went to the third store group change. Gosh, it confuses me so much. So 4 groups, 10 participants in each group. The dependent variable was how much time people spend in a store, and the hypothesis is that there will be a difference between different store layouts on how long people spend in there. So the store layout will have an effect on how long potential consumers will stay in the store. This is the data set. So we have our control group, or people who went to the standard store layout, and then we have our 3 experimental groups, which went to the first store, second store, and third store. The design of the study is between participants' design. The factor is store layout, and this factor has 4 levels. The dependent variable is time spent in store. To complete the analysis, there are 4 steps that need to be taken. Firstly, you need to check the assumptions of ANOVA. Does your data satisfy those assumptions? Second, you need to compute the descriptive statistics, then compute inferential statistics, and then do any additional analysis to understand the results of your inferential statistics. So in SPSS, to test the assumptions, you will need to use one function. Usually it's through analyze, descriptive statistics, explore, and then to test all other or compute all other, which is descriptive statistics, inferential statistics, and post hoc tests, you can do them all in Univariate ANOVA. So let's have a look at our data set. So the layout of the data set, we have our group and we have our time. So if we look at how variables are coded, we can see that this is a group, and we have our control group, store 1, store 2, and store 3. And it's a nominal variable because it's a group. And then we have time, which is a scale. So firstly, we need to test our assumptions about the distribution of the dependent variable. We already satisfy all other design-related assumptions, and the assumptions about homogeneity of variances can be tested as part of the ANOVA test. So we go to Analyze Descriptive Statistics, Explore, and we place our time variable into the dependent list because it's a dependent variable, and we'll place group into our factor list. First, we need to screen for the outliers, and second, we want to have plots. Usually it's better to have histogram because you can see if it's a bell-shaped curve distribution of your data, and we want normality plots with tests. Press continue and press OK. Okay, so let's make it look a bit prettier. What we see, the first table, case processing, so there are no missing values. From descriptive statistics table, at this moment we are only interested in skewness and kurtosis, and those guys seem to be in range, kind of, they're not too bad, there is nothing very concerning. So we would want then to go to the test of normality and see what they say. So all the tests of normality, the Shapiro, Wilk, and Kolmogorov-Smirnov showed non-significant result, which means distribution of our dependent variable is not different from the normal distribution. And this is the case for 4 of the conditions. Okay, so this one, it doesn't necessarily perfectly resembles normal distribution, but it's bearable. This one, in a way, could go more or less normally distributed. This one is much better. You can quite clearly see that there is more of a normal distribution, and this one also a bit better. But overall, so far, no concerns. In terms of the QQ plots, you want the lines to land, you want the dots to land on the line, or to be very, very close to it. So far, we have some concerns, but ANOVA is a robust technique that can deal with some deviations. Same in here, a bit better, and this one a bit better. Okay, the other interesting plots we want to see is this one. Okay, so we have one outlier identified in our fourth group, which is a store 3. And this person seemed to be out of the range. However, I would keep that individual in a data set, and the reason for it is when outliers are presented by the circle, they use 1.5 rule in SPSS, and because our Kolmogorov, Smirnov, and Shapiro-Wilk did not show any concern with the distribution of the data, I would keep that guy in there I mean, you can remove it, or that participant. You can remove that participant and see how it impacts your results, but it shouldn't be a particular concern at this stage. Okay, so the first analysis is done, and we satisfy the assumptions about the outliers and the assumptions about the distribution of the dependent variable. One more thing about the outlier. If this was a star, it was denoted by a little star, that person definitely has to be removed from the data set. So now we can proceed to conducting actual analysis. So if we go to analyze a general linear model, univariate, and we'll place our dependent variable into dependent variable box and our grouping variable into the fixed factors, because we're using all the factors we wanted to use. We're not randomly subselecting levels of the factor. And then we need to ask, it's usually good to ask for the plots to see the graphical representation of the data. So we want to place group on our horizontal axis, add it, and you don't have to have it as a line chart, you can choose a bar chart. Continue. And then we want to do the post hoc. This video is concerned about the post hoc. So when we'll go to the post hoc menu, we move our group to the post hoc test box, and the most commonly used test is the Tukey. The other test that we may be interested in doing is the Dunnett test. And let's have a look at the other one, which is this one. REGWQ is the second kind of more commonly used test. And the second test is much more powerful than Tukey, although it is a bit complex to read. And the Dunnett's test, just for the demonstration purposes, we want to say that all the groups will be different from the first group, and our first group is the control. So you can basically do it either from the first or from the last group. So when you create your data set and you already think that you want to use Dunnett test to analyze any pairwise differences between levels of the factor and the control group, it's better to do it this way. We are not predicting whether it's going to be like control will be less than all other groups or control will be more than all other groups. So we make no prediction, so it's a two-tailed test. Now, it's important to remember when you do the analysis, you only need to pick one of the tests. I'm picking three purely for the demonstration purposes. You never have to report all three analyses. You only stick with one. So if you're doing a task and toolkit test is your preferred option, you just stick the toolkit test and you continue. Okay, continue. Now the next thing we want is in options. We need to select descriptive statistics, and we also need to test homogeneity of variances test. You can select effect size for one factor. Designs, they're quite easy to interpret, and you would just say that this is the percentage of variance this factor explains in the dependent variable. Let's select it. Continue, and all is set. Okay, and wait. SPSS takes forever, we may as well have a coffee. Okay, univariate analysis. So the first table just presents to you the groups, kind of what are the between subjects factors and what are their levels. Then we have our descriptive statistics. So from descriptive statistics, what we can see is in store layout 3, which is our fourth group, participants spend much less time in stores than in any other group. But again, we can see that there is some variation in time people spend, but we don't know necessarily if it's significant or kind of between which levels of the factor, between which pairs there is a difference. Then we have our Levine's test for testing the assumptions. The result is not significant, so basically we conclude that the assumptions of homogeneity of variances is satisfied. And here's the main result of the ANOVA. So we have our group, which is our factor, and overall result is significant, and the store layout overall explains 57.8% of variance in time people spent within the store. Now we want to look at the multiple comparisons that we are selected. So the first one is our Tukey's test. So what we have is our control group compared to S1, and the result is not significant. So the control group and store layout 1 are not significant. The control group and store layout 2 is significant. The control group and store layout 3 is not significant. Now we want to know how the store 1 compared to store 2, and result is not significant, and store 1 compared to store 3, the result is significant. Store 2 compared to store 3, the result is significant, and store 3, yeah, that's it. No more comparisons. So because it provides a lot of same information, you don't need to report all the values. You just report for the comparisons you're doing. So it's 1 versus 2, 1 versus 3, 1 versus 4, 2 versus 3, 2 versus 4, and 3 versus 4. So 6 comparisons altogether, so you're interested in 6 values in there. Then below in here we have a Dataset test, and that's where we compare control to every other new store layout. So in this case, what we can see that control group is only different from the store 2. Again, you don't need to select 2K Dataset test at the same time. It's purely for the demonstration. So if you have a prediction that a store layout will be better than the control layout, and this is what you want to test, then Dunnett's test is a more suitable test for you rather than Tukey test. And the reason for that is because of the family-wise error that it controls for. Now, back to the Tukey-HT. It comes with the homogeneous subsets table. And this one presents exactly the same information as the Tukey's test table, but the way you read the information is the pairs of means in the same column are just not to be significantly different. So what we have, one and group one, or let's call it, group one and group four, which is a store 3, is not significant. Group 1 and group 2 are not significant. Yeah, we have our pairs of means. The group 1 and group 3 are significant. There are no pairs of values. Group 2 and group 3 are not significant. We have our pairs. And group 2 and 4 are significant, and group 3 and 4 are significant. So this table, again, is not intuitive to read, and basically because we have these empty spots in here, we'll judge tests as not significant. The same principle, so basically for the same principle applies for the REGWQ test, reading the output, but it's just kind of, you don't have a more explicit table to determine the results. Now this is our plot. Ryan, Elliott, Gabriel, and Welsh test. So the remark difference between the Tukey's test and the Ryan, Elliott, Gabriel's Welsh test is that this value in this box is missing. So what this test found for us, that there is indeed a significance difference between groups 2 and 3. Yeah, you see this pair of means is missing. And that is why Ryan, Elliott, Gabriel, Welsh range test is much stronger. It's more powerful. It will spot the differences if there is one. So when you do just a Tukey test, it's quite conservative. It uses, in a way, the Ben-Ferroni adjustment to adjust for the family-wise error. This test uses slightly different, slightly adjusted rule for computation, and therefore can be more powerful. And the last bit is our plots. So this one you can format to make it look pretty and place it in a report if it has any additional information and helps the interpretation of the results. Usually, because we report means and standard deviations, this graph is not necessarily informative to be presented in a report, but just for you to see how groups performed. If you're a visual person, reading information from the graph could be just easier. This is it for the multiple comparisons for univariate ANOVA.